This is Jack Jackson. In this video, we're going to talk about another discrete distribution called a Poisson distribution. So in a Poisson distribution, here are some of the things that are going on. We let x be the number of occurrence of an event over a fixed interval. And the interval might be time or distance, area, volume, weight. There's some different things that it could be over. And what we have is the probability of an event is the same for all units of the same size. For example, the probability of an event occurring in any 5-second interval is the same, regardless of which 5-second interval is chosen. The number of events in a particular unit is independent of the number of events occurring in another unit. So again, if we're looking at a 5-second interval, a 5-second interval from now to 5 seconds later, the probability of an event happening there is the same as the probability of an event, 3 days from now, a 5-second interval. And that's independent of what happened here in this one. And occurrences are random and uniformly distributed within the interval. And then if with those assumptions, the formula for the PDF of x is mu to the x power times e to the minus mu over x factorial. And the e is the same e that we use for exponentials in our algebra classes. And the mu is the mean, so that's why I call it mu. You're going to see it called lambda, this Greek letter here, lambda, much of the time. But I prefer just to call it mu because it is the mean. And so it turns out that this lambda or mu is actually the mean. It also turns out to be the variance in this case. So this one has the same mean, the same variance. And it turns out the skewness is 1 over the square root of mu. And x can be any whole number. And notice that the PDF of x decreases as x increases. So, the height of the bars is going down. So in that sense, it's kind of like an exponential or a geometric, that the bars are getting smaller as we go on out. Okay, and so this is the formula that we're going to use. So what's the formula for the PDF of a Poisson distribution with mean 10? And by the way, this mean is also the average occurrence rate. So you just plug in the 10 in place of the mu there and there. This e to the minus 10 is a constant then, and then the variable x is the power here on the 10 as in the base down here in the denominator. It's the input for this exponential. And this turns out to be that. Construct a PDF table and CDF table from 0 to 10. And this here it is here. Now, like the geometric distribution, this goes on forever. The geometric distribution went 1, 2, 3 up forever, all the natural numbers. You can have 0 for a Poisson, but there's no upper limit. It goes on forever. So notice the CDF hasn't quite made it up to 1 yet. In fact, we're not really even that close yet. We're only about 58% up through 10. So the rate of occurrences is 10. The mean is 10. The variance is 10. So the mu is all of those things. The standard deviation then is the square root of 10, or about 3.16. And 1 over the standard deviation turns out to be the skewness. So it's all kind of based on that one parameter. With a pretty easy formulas there. So anyway, there's there we go. Now, it turns out that there is a Poisson CDF and a Poisson PDF built into both the TI-84 and the Inspire calculators. So here's the 84 version. It's between the binomial and the geometric in the list here. So there's the Poisson PDF and the Poisson CDF, and they work like you would think. You have to give it, the defining parameter is what I'm calling mu or lambda. It's the mean or the average occurrence rate. So if I do Poisson, I did Y1 is Poisson PDF of 10, x. Y2 would be Poisson CDF of 10, x, and then I set up my table to start at 0 and going out by 1s. That generates a PDF and CDF tables. The PDF values are in Y1, the CDFs are in Y2. And if I graph it, it looks like this. So it kind of looks more like a binomial. It goes up and back down, but then the bars go out forever. Eventually, it's going to go on out. The bars are going to get smaller and smaller as you go way out here to the right. But they may start small, go up, and come back down. So it looks a lot like a binomial, right? At least for this part of it right in here. And here's kind of part of the CDF look of it. So what are some examples where this might be used in real-world settings? Well, here are a couple of few settings that are often modeled well by Poisson distribution. The number of traffic accidents per month at a particular intersection might be modeled by Poisson probability. The number of surface defects on a new automobile. The amount of toxin found in a water or air in a plant in parts per million. The number of diseased trees per acre of a certain woodland. The number of death claims received per day by an insurance company. And the number of unscheduled admissions per day to a hospital. Notice it's always per something, right? So traffic accidents per month. So month is our sort of our time interval there, our interval. Surface defects per automobile. Parts per million of a toxin. Number of diseased trees per acre. So it's always per something, per day on these last two. So here's another real-world application. Suppose that the number of unscheduled admissions per week in a hospital is 20 patients, regardless of the week. What's the probability that the number of unscheduled patients admitted next week will be exactly 7, less than 10, more than 29, or between 10 and 30 inclusive? Well, this setup is Poisson, and the 20 per week is your mu. Okay, and so we can work that out. Exactly 17 would be a Poisson PDF. Remember, PDFs are always exactly equal to, so it's a Poisson PDF of 20, 17. Less than 10 will be a Poisson CDF up to 9, because it's strictly less than 10. So that's from 20 to 9. Remember the X value here, it has to be a whole number, right? So there's no probability or zero probability between 9 and 10. So that's Poisson CDF 20 to 9, or 20, 9. That's from 0 to 9 is what it really is. More than 29 is above 29, so you're gonna it's a probability to the right. We want to find the CDF gives us a probability to the left, so it's 1 minus Poisson CDF 20, 29, which is there. And between 10 and 30, including the 10 and 30, we would go all the way up to 30 by doing the Poisson CDF 20, 30. And we subtract off the probability that it's between 0 and 9, which is a Poisson CDF of 20, 9. At least that's the way that calculator works. So if we use an Inspire, as you see here, then it works. The CDF works very similar to the way it does all of its CDFs. So you go to Probability menu, then Probability Distributions, and somewhere down here is the Poisson. Say the Poisson's, the PDF here. It asks for lambda, which is the same as mu, which was 20 in this case. And it asks for an X value, which is, we did exactly 17. And so we would do that. So it's Poisson PDF with a mean or lambda of 20. And we're trying to find the probability that X is exactly 17. There it is. And then we can also do, this should agree with what we did before. We need that twice. Let's get rid of that. And then we can do the Poisson CDF, Probability Distributions, Poisson CDF. And the way the CDF works here, just like it does all CDFs, it's not a true CDF. It gives you the probability not just to the left forever, but between the two values. So if you'd leave this 0 all the time and then just change this number, then you'd have a true CDF. Less than 10 is actually from 0 to 9 here. And we can get that probability. Whereas if we go here and do the next question, lambda was 20, lambda or mu, and we're more than 29. Now here, you still have to use, the problem is there's no upper bound, so we can't go from, we could go from, we want to go from 30 to infinity, but we really don't want to put in an infinity, so we're still going to need to do 0 to 29, and then we want to do 1 minus that. So we want to do 1 minus, copy, Control C, down here, Control V. So we wanted to do that as a 1 minus like we do it on the TI-84. Notice that on the binomial, for example, there was always an upper bound there, so there wasn't that there was, you know, you can't get more successes in the sample than you have items in the sample. So there was a hard upper limit there, but this one goes on forever, so we can't. We have to do it this way with the 1 minus. Okay, and then between 10 and 30 inclusive, that's the way this one's really set up nicely to do. And so this works very nicely here. PoissonCDF, again 20 here, and we're going to include 10 is the lowest one we're going to include. We're going to include 30, which is the upper one we're going to include, and we're going to include everything in between, and that's exactly what that works out to give us. Okay, and there's the there it is again with the 3 screens from the TI-84 and the screen from the Inspire as well. So there's the idea of the Poisson. For my particular class, I'm going to put the Poisson on the practice test or the exam, but it will be on a couple of homework problems. So you'll have to work with it there, but you don't have to really worry about it so much on the exam just because we're kind of running out of time here for the end of this unit.